us here today. We'll go ahead and get started with this opening session of the joint MPAS WRF workshop. As a member of the NOAA Global Systems Lab, it's a pleasure to be here to be able to introduce a number of short lectures on NOAA contributions, many of which are related to MPAS. For reference for our speakers here, we have 35 minutes for each of your talks, 30 minutes for the presentation, and 5 minutes for Q&A. There will be a timer there that will turn red at 30 minutes. It will turn yellow at some undefined point between 0 and 30 minutes. We'll find out with our first talk just what number that is. We also have a pointer here for those of you speaking. If you hold down this top button and point it at this screen, not up there or over there, you'll get a laser pointer that you can use to highlight particular features on your slide. So with that, it's my pleasure to introduce our first speaker of the session, George Grell, speaking of a new or old version, now here specifically updated version, of the Grell-Freitas, now Grell-Freitas-Li scheme in WRF, MPAS, and UFS. George?
Yeah, so this is a talk about getting rid of the multiverse of GF schemes. Wanted to see. And the reason it's GFL now is because we have to thank the L in the GFL scheme for actually doing the work to make it not multiverse anymore. Now I'll talk about that a little bit more. Okay, like I said, it's a multiverse. There were different GF versions in WRF, MPAS, and UFS. So I'm going to talk about that a little bit first. I'm going to give you a little bit of an introduction about what's new in the latest version, which is the most we considered. It doesn't mean that's really the case. We consider it the most advanced version. And that includes evaluation of simple aerosol awareness, new scale-aware approach, that's only in MPAS available, and simple cold pool approaches. And that already means, will all options work in all models? We don't know. But they're all implemented anyway. Well, I'll talk about that. And then in the future, we change the name again. We are converging to C3P, and I'll tell you a little bit about what that's going to be too. And that might be in a different lane than GFL, though. It's just then, again, the development on GFL will stop as we go to C3P. A little bit of background here. GF can use stochastics to change heating and drying profiles in a mass-conserving way. That's been tried by very few people only. The 2014 paper describes how aerosol awareness should function. It's being evaluated now, and the paper is going to be submitted very soon on that. That's from Li. Scale awareness is the original is based on Arakawa approach. And again, we have something new there. WRF, MPAS, and UFS all use different versions of GF that needed to change. MPAS actually uses the very old version. WRF, for some reason, uses something that is very similar to the latest version. Not close, but it's much more similar. We're kind of accusing each other who actually updated this thing over the last 10 years or so. So it wasn't me. And Li converted the most advanced version of GF, most advanced, we hope, into a submodule, which is independent of the host model. So the same version can now be used in all modeling systems. One thing that still needs to be done there is we still need the drivers be taken out of this. What's new? GF uses the characteristic cloud size to describe deep and shallow convection. That's in MPAS 2. And original implementation didn't use a PDF, and the scale-aware approach is a very original way to do it. It decreased the characteristic cloud size when a certain area coverage was reached. So it we tried in a hurricane simulation down to 1 kilometer, it kind of became like a shallow scheme at that point. And we're not using that anymore. WRF and UFS versions use a characteristic cloud size for deep, shallow, and congested clouds, so 3 plumes. And the average statistical mass flux properties from those characteristic cloud sizes are described by different PDFs, beta functions. For deep, shallow, congestus cloud, entrainment, detrainment then follows from the mass flux distribution. So we're not making assumptions of what the entrainment and detrainment looks like. We're just making assumptions about what the mass flux looks like, where the maximum is base at the top, and then derive the resulting entrainment, detrainment. Level of maximum mass flux for deep convection determined by stability profile. For shallow convection, just at or above convective cloud-based. That seemed to work pretty well. Congestus is always a little bit questionable. Just an example for shallow convection, comparing the beta PDF, so to the Bomex, Siebesmite, all cases. It comes out pretty well. For deep convection, it also comes out pretty well if you compare the dashed red line with the black line. What we're assuming there is that the maximum mass flux is reached just at or above the maximum instability. That seems to work. So more new developments. Memory may be used to influence the PDFs. Cloud water detrainment also. That's turned on actually in the older WRF version, I believe. But it's turned off in the new GFL versions. Don't ask me why. As we were usually trying to manage to beat GFS scores, and we were constantly tuning and modifying and trying things, so that's probably why it's turned off. Anybody has any questions, we can certainly answer questions, we hope. Mixed phase microphysics considerations, that is currently only in UFS, but it's now also in all versions. Like I said, the new GFL version has it in there. We were hoping to see a bigger impact from that. Invigoration, for example, especially once we also included the aerosol effect. The problem was the stability in the upper levels is so strong that it barely made any impact if you assume the usual stability criterion of equality there. If you let it be a little bit flexible, then you'll see more of an impact. We have a routine that does below cloud-based evaporation. That's optional. And then for cloud water and ice, to avoid negative mixing ratio, we changed the subsidence terms by using an upstream form. We have a choice of using a flux-corrected transport scheme, positive definite. We were not really happy with that. We just leave that out. We're just doing simple diffusive upstream differencing for that. Now comes the new one, aerosol interactions, and all those new things I'm going to show some slides on. Include transport wet scavenging, but also impacts on microphysics of the convection parameterization. And that's a paper that's currently in internal review from Hai-Chin Lee as first author. A new scale awareness approach is being evaluated currently only in MPAS. The problem is that it needs communication across the grid points. That was especially with Bill Skamrock's help and Michael Duda's help. It was easy to implement in MPAS. Good luck with UFS. And we haven't, WRF should be not too difficult if somebody actually wants to attempt that. Cloud movement and downdraft cold pool advection methods are being tested. These are simpler versions of the Grell-Freitas et al. Approach, and he talks about that on Thursday. Aerosol awareness first. So we have like 3 things in there that we modified. Now we have to try to keep it as simple as possible. And you have to remember in convective parameterization, usually they use a constant conversion rate, no time change. And very similar for the evaporation that impacts the downdraft strength. It's a very important parameter in the parameterization scheme. So the change 1 is just to do a simple Berry conversion. We can use any other conversion, that's not a big deal, to impact the conversion of cloud water to rain. And the second one is we modified the evaporation of raindrops based on an empirical relationship. Pretty much only means the precipitation efficiency is changed. And then the third one, after talking to Feingold, Graham Feingold, we also implemented scavenging through memory based on the paper by Lee and Feingold. Now, both of these changes, change 1 and change 2, require proportionality constant that tell us they tell us pretty much what you would get if you would assume that the constant conversion rate, which is C naught in those parameterizations, was derived under averaged conditions of AOD or CCN. So it is a very simple approach. And what we see then, this shows you an example of prognostic aerosols. This is all using prognostic aerosols, but very simple, only biomass burning, dust, and anthropogenic emissions. And what the AOD would look like using those prognostic aerosols versus the background value of AOD that we used, that was calculated for MERA2 climatology, which in this case is 0.14. So whenever it's red, it's higher than 0.14, blue, it's lower than that. And you see, that's actually, for this particular case, that's of course dependable on the situation and time of the year. There's some areas where some pretty significant differences. You look at the precipitation efficiency, and what you see is that in the aerosol high regions, precipitation efficiency is lower, while in the aerosol low regions, precipitation efficiency is higher. That's kind of what we were hoping to see. And so that's good. This is an average over 10 cases at 2 different valid times, 6 hours, 120 hours. We did this because wet scavenging plays an influence. And usually that impact comes much more out in the polluted areas because it removes it, unless you get strong emission sources all the time. For example, you can see that clearly over India too, where it changes from negative to positive. Vertically integrated cloud ice, that's from the conversion from cloud to ice, cloud to rain. You can also see that there's much more output of cloud water and ice in the aerosol regions. That's again physically realistic. That's what we were hoping to see. And again, this is only, what we're trying to do is to make sure we're only looking that the parameterization impacts the extreme events. So that's why the most of them here you actually see in the very high pollution regions. Hai-Chin has also looked at just a couple of different cases for rain observations and whether it's luck or not, but for these cases actually results with the aerosol effect turn out to be better than the ones without. Now the whole model was run with the prognostic aerosols. It's only GFL scheme in this case that is either run with the old version or with a new version. Everything else is identical. So a simplistic approach appears to give reasonably physically acceptable results. Aerosol concentration will lead to more cloud water and ice detrainment at upper levels. The concentrations may impact precipitation efficiency, especially more likely for the very low, the clean cases. But requirement, of course, you have to never forget that. This only makes any sense if you're able to predict or analyze aerosol concentrations with enough accuracy to do better than climatology. So for the very long-range predictions, that makes this very difficult because it's still very difficult to predict aerosol concentrations with reasonable accuracy. However, for strong aerosol sources, dust, smoke, for example, and for shorter time focus, just look at her smoke, this is not difficult to do. Will it run with WRF? We just, like I said, Hai-Chin just implemented this. We just made a very quick test run with AOD constant everywhere in the domain, 0.005, very clean, 0.1 average, and 1 very polluted, and the precip sure shows the same kind of behavior. Now a new approach to implement scale awareness in convective parameterizations. Many thanks here to Michael Duda and Bill Skamrock for providing assistance to get this moved very quickly into MPAS. It must be very easy to work with that model. You try this with UFS, good luck. So this is the original conceptual idea of how convection cloud may be seen in a parameterization, where you get lateral mixing and detrainment and from downdraft and updraft, and then the subsidence. Now, yeah, if you're on a 50-kilometer grid, that's fine. If you're anything smaller than 10 or so, then usually we all know that this is not going to happen all in one grid box. There's various approaches to handle this out there in the community. Started with UK Met Office in the 80s. And even the G3D scheme, if you remember that one, if somebody's still using it in WRF. But that's, they're all kind of half-hearted implementation of the idea that we followed in this case. And that is that we assume the lateral enchainment, detrainment happens in that grid box, but the cumulus-induced subsidence is being spread out to actually 2 grid points in this case. So the original one, maybe I shouldn't even talk about this one for time, but if you look at the, and oh, you can see that, cool. This term is kind of the original solution for the vertical eddy fluxes. And then to get the new eddy fluxes, what Arakawa does in this case, there's a fractional area covered by the active cloud draft, the sigma, and there's 1 minus sigma square is being applied as a scaling factor. That's used by many different convective parameterization. They may not mention this 1 minus sigma square, but they do scaling to have the parameterization turn itself over to the explicit microphysics. And of course, numerical, that's a nice assumption. Physically, it's really nonsense in a way. That's not what happens physically. So should convective tendencies be really scaled? If you think about it, a fractional area coverage would be 90%. The scaling factor would be 0.01. So where you have a big storm, the convection scheme thinks there's like a big storm developing. You scale this down by 0.01 and you're left with minuscule, tiny little precip amounts. So the new scale awareness, the compensating terms are now distributed linearly over 2 rows of neighboring grid points. I'm not going to talk much about these. You can read them if you want. And we use the Arakawa approach to determine how much should be spread over what grid points. So the requirement, of course, is tendencies due to compensating mass fluxes had to be separated from the feedback tendencies and kept as separate 3D arrays. And that's the same for the compensating uplifting from downdrafts. This can be done for any parameterization. This is not dependent on GF. You can use that for Tietke. For whenever you can separate these tendencies, it's easy to do. So no scaling is applied on any of the tendencies coming from GFL on whatever resolution. So one question was also, will that approach be able to smoothly transition from non-resolved to resolved convection, or is the scaling necessary? That's just another picture. This is the original approach with updraft and downdraft all in one grid box, as well as the environmental subsidence, which, as by the way, is a very strong drying and heating tendency, and will very much try to avoid keeping your microphysics active. So if you don't do the scaling, you're going to be in trouble if you just have it all in one box. And the new approach then just spreads the subsidence over many. In this case, it shows only 1 grid point out, but we actually use 2 grid points out. There's one example of 5-kilometer delta X MPAS simulation. The upper 2 are the old scale-aware approach, and what you can see here, which is the annoying part, you can see a lot of convective parameterization activity in the storm center, which is really not what you want to get, because it decreases your storm intensity, and it just messes up with the structure of the storm too, because it's a parameterization. It's not built to handle a big tropical cyclone. With the new scalar approach, you can already see The centers are clean of convective parameterization. There's more precip out in areas where there's not that much in the old scalar approach. This is just a shot that looks at it in greater details, just to show you. Actually, you see that the center is actually more intense, and again, the precip there from the convection in the center of the cyclone is not a good thing. And as a result, if you look at the cross sections, I don't know whoever developed those cross sections for MPAS. I should buy him a beer, because I hate to do that myself. But again, it's a really nice comparison. You can see that the structure is much more defined at the 5 kilometer resolution. Going to 3 kilometer, come on, why is it not going? Okay. All right, it doesn't want to move. Can you move me forward? No, only one. Go back. There. Up. Yep, one more down. There. Okay, for 3 kilometer, it's very similar results, but here you can see that the precip amounts in the 3 kilometer result from the convection parameterization still are at the same level, while at the 3 kilometer old scalar approach, they become very small. Okay, now it works again. So again, this might be a better alternative approach. It works in MPAS, in none of the other models. Physically unrealistic to scale down the tendencies in rain rates by large factors. Without scaling, subsidence usually is strong drying and heating term. If it is applied in just one grid box, it tends to prevent the microphysics from becoming active because it dries so strong and heats. So lateral mixing in the inner grid without the heating and drying from the subsidence actually turns it over much quicker, which is why we see much less activity inside the storm, because the parameterization has turned it over to the explicit scheme quicker. In the near future, we will switch to the Freitas-Li GF version. That's a C3P again. And implement dimensional prognostic area fraction calculations and our new stuff. And then we call it C3P. I'm going to mention that again. All right, and the next one is on cold pools. This is just one example. Saulo will talk about this a little bit more detail in his version. You can really see in the, not only here in the Amazon region, also look out here in the Pacific. In the tropics, it seems to be a very, very important fact for organizing convection, which is why we got involved in this. And actually, if you look at the lower part here, previous work by Hannah Barnes, she gave talk in the WRF workshop here before, and in other international talks. She used what we had first, which was a similar idea as in Frank and Cohen paper, 1984, but with a downstream component, which we added in the GD scheme in 2002, where we just have an equation for downdraft mass flux increment. This is just a WRF simulation here that shows you how that works with the potential temperature difference clearly stronger developing in the movement direction, and the movement actually is a little faster. The original idea behind this was to make sure convection, for example, quite often in global models, you have convection developing over mountain areas and not moving away. You could see that here in Colorado quite often. That's just nonsense. With a flow, it will move away. Unless your forcing actually moves, the convection cannot handle that. So this would avoid that. That's why we originally started doing this. And Saulo then did this in a much more rigorous way by developing a prognostic equation for buoyancy access. He'll be talking about that, so I don't need to talk much about that. What we use from that very simple approach. For one, this gets a gas front velocity. We can apply that to the surface fluxes. That's one way. of implementing this impact. And then the other one is an additional momentum tendency is being added that is proportional to the gust front speed and the assumed movement speed of the convective elements. So this does both. It just increases your dependence, your forcing for the downstream convection, as well as keeping on moving the convection without doing too much other work. You can also, of course, use this WRF, the maximum vertical velocity at the leading edge of the cold front, to have additional forcing being added. There's a lot of stuff you can do. We decided on just these two simple approach, really simple here. And we'll have Saulo do the complex stuff. This is just very initial work. We've just been looking at that. The heat flux differences are too small, actually, but I think the problem is, and I talked to Joe about that, that probably the surface flux stuff is being overwritten again somewhere. Otherwise, sea level pressure differences just show different movement speed, but otherwise not too much difference. So this is available in all models, but it's not tested. And you have to kind of know what parameter you have to change. So we keep that a secret, it's job security, I guess. Once we move to Saulo's version, it's different because he has a very different name list just for the DF convective parameterization that has pretty much all those parameters in there. So Saulo's version is optimized and cleaned up, including the separate long name list just for GF or GFL with all changeable or tunable parameters. And Saulo's version also has different microphysics options. It has a lightning parameterization, the more complex cold pool parameterization, that big equation I showed you before. Chabot-Bechtold radiation coupling that is already in GFL now. And then many useful options for chemistry applications, both for aerosol as well as gas phase chemistry, especially with respect to wet scavenging for the gas phase chemistry. There is an option for timescale removal based on the subglacial vertical velocity for stability closures. Impact of relative humidity on the diurnal cycle based on Tian et al. 2022 GRL paper. That's only for diurnal cycle closure. I don't think anybody ever used. Ice liquid fraction based on MODIS data just for both inside the scheme as well as outside in the driver to determine which one goes into cloud water, which one goes into ice. And then, as I mentioned, we will move aerosol-dependent simple cold pool parameterizations into his versions. And that work will start next week. Saulo is here for 2 weeks. And then Lisa Bengtson from PSL is implementing the prognostic fractional area coverage approach that's currently also used in SAS into C3P. And finally, the scheme will then be renamed again to C3P, which stands for Community Convective Cloud Parameterization. Development, NOAA GSL, PSL, and CPTEC in P. Questions?
All right, we'll take questions from in the room and online as they appear. For those in the room, like Lou is already up at the microphone, please take his lead and come to one of the microphones in the center portions of the room. All right, Lou, go ahead.
So, George, I was wondering if you go back to the aerosol work and the ice concentrations, did you guys actually look at whether or not there was a feedback from your increased or decreased ice concentrations with the aerosols to the radiation? Way back at the beginning, sorry, yeah. Like that, yeah.
Cloud water ice.
Yeah, I mean, did you look at radiation? Did anybody look at the radiation
Oh, yeah,
effects?
we did. It's a big difference. We're kind of hesitant a little bit. I mean, Hai-Chin wanted to show this because the GFS looks so bad in this that I didn't want to show that. It's really much better, but, you know, it always depends on what version of GFS you compare to.
Right.
And
Right.
I really here wanted to focus only on what the scheme does, not necessarily to observations, right? I mean,
Well, I'm just saying, in the tropics, getting the radiation is really better, and I agree the observations are important. I mean, I think that's the feedback effects that extend beyond just the scheme itself, I think are really potentially important too, so,
right.
anyway.
I mean, there's so many different things involved here, though. You know,
Oh, yeah.
it's a question of how does the microphysics respond. And it did look significantly better. It was, we were too shy to show it. Come on, guys, I gave you time. I mean, I ended up 1 minute early.
Yes, so I wanted to ask, it might be a very stupid question. The 10-kilometer horizontal resolution, let's say once you start to reach, you have parameterizations that start to fail. Is there like a vertical resolution as well, after which the parameterization that is given by such cumulus schemes starts to falter, or like it keeps increasing no matter how much dz becomes smaller?
You're talking about the scale awareness, right?
Yes.
We don't care what the resolution is. We always apply this. It's just when it's coarse resolution, I mean, most of the substance is still going to be in that grid point. It depends on the fractional coverage. Vertical resolution is not impacted at all. We don't care.
Okay. Is there a reason as to why the vertical resolution does not matter at all, even though the
No, I don't know whether there's a reason. I mean, the only reason is we're not funded for that work. I'm officially retired right now.
Okay. Got it. All right, thank you.
You said you turned the cloud water detrainment off at one point there. So
Turned what?
Cloud water detrainment or cloud detrainment? You
No, I didn't turn off anything.
What did you said something about the cloud detrainment doing some
What I
harm
do
to-
is we have a mass flux. We determine a mass flux, and then we derive the entrainment and detrainment. So the initial entrainment is given by the cloud size, right, that 0.2 over R relationship. And then we know till you get to the mass flux maximum, we have entrainment, but not much detrainment. And then afterwards, we increase the detrainment, but leave the entrainment.
So you do keep cloud detrainment.
Oh.
Okay. I had the impression you said you didn't have cloud detrainment, cloud water, or
No, we do have cloud water detrainment. Cloud water ice, which is why you see these results right here, you know, because it's a lot more cloud water ice detrainment and aerosol. That it?
This question is more about applications. So what are your thoughts about the use of convective parameterization in 3-kilometer-ish applications in terms of maintaining fidelity of like severe storm morphology over the United States, but also making sure we represent tropics and other places with weaker forcing? So if we are to run a 3-kilometer model over the globe, is your scale awareness now going to...
That's a very good question, of course. I mean, you know, that has impacted me in the past, too, with Rufus, for example, version 1, right? I mean, you can improve by using a convective parameterization on 3-kilometer, even over the CONUS. You can improve your precip scores and other scores, especially once you go out past 24 hours. But you have the tendency, if you just use a scale awareness, the way it's in there, to destroy your probability of detection of the severe storms. They don't like that here. They want to predict more storms than less, rather. So that kind of what cost us GF in it, because they used the SAS scheme in that case with the usual scaling factor, which didn't do much. So that's why GF did not get into Rufus version 1. Overall, I think on 3-kilometer resolution, especially in the tropics, convection parameterization will still be very important. Saulo might talk about that a little bit too, I don't know. But it's, you know, 3-kilometer, you're maybe effective resolution of 10-kilometer or even worse. you need a convective parameterization there, but you need to make it smart. So it's whenever there is convective organization, it needs to turn it over to the explicit scheme.
All right. Well, we need to move on to our next presentation, so let's all thank George once again. And for Ted and all the remainder of our speakers, the yellow light on this is very faint, so if you want a warning ahead of the 30 minutes, feel free to let me know. In soccer fashion, I do have red, yellow card here as well, so otherwise with that, I'll turn it over to our next speaker, Ted Mansell from NSSL, to speak about the NSSL Multimoment Bulk Cloud Microphysics Scheme.
Should this be in full screen mode here, or is it?
Yeah, do you not want it in presenter mode?
Oh, well, I don't know if it points well or not. Doesn't matter.
Sounds good.
I'll be surprised at what the next slide is. But I want to start out thanking the organizers for putting together this special session for the NOAA Physics, and especially thank you for inviting all of us to participate. And so I guess we'll move to smaller scales here than what we just enjoyed from Georg. And I'm going to start out with a question. Do I have any Viz 5D fans here? 1, 2. This graphic is for you. That's good old Viz 5D. I keep it running on Mac OS. So the NSSL scheme has a kind of a long history. It almost starts with my PhD work back in the and back at OU, and when I did, well, I still do electrification modeling. So when you do electrification, you want your microphysics to be as fancy as possible, because you want to know number concentrations, you want to know all the things you can to get those particle interactions for electrification. And I appreciated the theme slide for the conference has a nice lightning strike in it, so I appreciate that's a very nice touch. So I've been in the field of storm modeling for quite some time, and that's a primary motivation for this research-oriented scheme. Our primary interest has always been convection that makes lightning, and that has expanded over time from severe storms to tropical cyclones and also ordinary storms. And the reason it's called the NSSL scheme is there are roots from Konrad Ziegler's work with retrievals of microphysics from radar analyses, and he had some nice work that DNA is woven into the code, along with a lot of contribution from Jerry Straka at the University of Oklahoma, where we started out with a multi-category single moment scheme that really actually did a pretty decent job, but really wanted to get number concentrations predicted, and there were a number of challenges in doing that. The NSSL scheme was first added to WRF back in version 3.4, and I don't know how long ago that was, but it seems like a long time. And then it's also appeared in other research models like CM1 and ARPS, and also added to the CCPP for use in the UFS. And like I just mentioned, it's a research-oriented code, but it has reasonable efficiency, and it's been used in real-time forecasting in our Warner and forecast system at NSSL. So what's special about this scheme? Well, one thing is it's fully two-moment. All species predict at least mass and number, and there is now an option to go to three-moment for the faster falling species, which gives better sedimentation. We'll see a lot more about that coming up. And for rapid development. There are no external lookup tables that have to be computed. And, oh yeah, it's fully two-moment. And WRF, you can still run it single moment if you really want to, for kicks. So sedimentation is something I'll talk about more, and there's some specific attention that's needed there for two-moment schemes. And having the multi-moment is important for predicting duopole radar variables. And I'll show a little bit of that too. George mentioned invigoration, and to do any kind of study with that, you need to predict your aerosols and your droplet number concentrations. And a lot of schemes use what's called a saturation adjustment to do condensation onto droplets. But in the Nessel scheme, we do an explicit condensation that can leave a residual supersaturation, and I'll show that shortly. Another feature is the prediction of bulk density of graupel hail. And the hail species itself, I'll talk about more, but it's intended as a true hail and characterized by size rather than the density. A lot of internal developer options you can get into, and most people don't. And it's also available, again, in multiple models. MPAS is pending, but I just found a paper today in QJRMS that actually uses the scheme in MPAS. No shade implied, but the pull request has been in process for a while, and so it's been available kind of on the side. Forward. I would say, okay, so a quick overview. We have kind of the typical species, but including predicting the number concentration of the cloud condensation nuclei, the CCN. We have droplets, rain, cloud ice, snow, graupel, hail, and in most of the models, the hail can be turned off if you're not doing severe weather or if you're doing a larger scale system. And then to get the particle volume, or get the particle density for graupel and hail, actually predict the volume, and then the density comes out as the ratio with the mass. And then for the three-moment scheme, we add the reflectivity moment, circled in red there, for the faster falling species. Got to have a couple equations. These are just the size distributions. But the main reason for showing this is to point out that there's a certain flexibility here that I've borrowed a lot from the Seifert and the Heng to be able to use different distributions for the different species, particularly in the, there it is. In the exponential term, there's this extra shape parameter, the mu here, that lets you do a size distribution of volume instead of just diameter. Okay, so into some actual pictures. So I mentioned the invigoration and the aerosol prediction. And this is an example from some work I did with Konrad Ziegler. And this is just a small storm, it's not severe. And on the upper panels, we have a low CCN concentration, and you get the fewer drops, larger droplets, faster warm rain production, and you get a higher residual supersaturation, which is hard to measure, so it's hard to say, hard to tell me that I'm wrong. And then when we add the higher CCN, we get what's the expected physical response. You get smaller droplets, slower warm rain process, and a lower supersaturation. Button straight. And that also comes into the graupel density, which is primarily driven by the rime density. And the rime density, here's one option, or default option. There are a number of laboratory studies with different equations, but the main thing here is the droplet diameter comes into play. As you have larger droplet diameter, you get higher density. And then the ice density is also affected by the wet growth, melting, where we assume that there's some soaking into the particle. And what this does for us is that Graupel category is really a Graupel/frozen drops category, because it can have characteristics of low density Graupel from an ice process of rimed ice or snow, or you can have high density frozen drops from rain freezing. And then that leaves us free to have our hail category be defined by size instead of the density. Here's an example from that same paper with Conrad, showing how the Graupel density can change with the CCN, because you're getting smaller droplets, and then you get, as you have higher CCN, here the kind of ridiculous value of 5,000, but it makes the point that these smaller droplets give you lower density riming and also change you over from a warm rain process into an ice process. So we're starting out at the low CCN, we have very high Graupel densities, over 700 all the way through, and then we, at the other end extreme, we get low densities below 400. And something else that density prediction gives us is a variability in the fall speeds. So it gives us diversity of fall speeds. And the original option that I made was based on work with Jerry Straka. And those are the solid lines here, just adjusting the fall speeds based on the density through the drag coefficient. And then some more careful work was done by Milbart and Morrison, 2013. Those are the dashed curves relating the same quantities. And they look pretty similar here. If you look at the smaller sizes, though, there's a definite difference in the high density, where the original values are definitely higher than the 2013 values. And you might think, well, that's not a whole lot different. What does it really look like in a storm? Well, on the left is using those solid curves, and on the right, everything else being equal, is using the dashed curves. And there's a clear difference, especially for those high density falling hydrometeors. With those faster fall speeds, we have significantly more precipitation reaching the ground. We have stronger cold pool development and higher reflectivities, whereas with the lower fall speeds, you get less. And if you just change each of these by 10, 15%, you can actually see a somewhat dramatic difference, which is a little bit scary, actually, but it gives us room also for creating ensemble diversity through the physics if we have single physics schemes. So on to hail. There are a number of schemes that have what they call separate Graupel and hail categories, but those are largely differentiated by density. So they have fixed density, a low density Graupel, and a high density hail, which is really more of a frozen drops at the smaller size. And one issue that you run into there is when you define by density, then your frozen drops go into the hail category and can keep your hail sizes rather small, and you end up with very little accumulation of solid ice at the surface. So what's different about the Nestle scheme is we try to take the only source of hail coming from the large Graupel. So we convert the large Graupel into hail, and then we can maintain two very different size distributions simultaneously. And both of these categories are treated the same in the model. They have the same density-dependent fall speeds and the same equations for growth. The hail is also limited in how dense it can be, or on the low end, but it doesn't usually reach that anyway. And I could be proven wrong, but I think it's pretty hard to physically represent hail just within a single size spectrum, a single category. I might have convinced Anders of this. Yeah. Maybe we'll see what he's up to. So here's just a little graphic of how this works. So here's a hypothetical size distribution for the grapple. We have some deconvert, and anything larger than that, we just do an integral and convert the mass, the Q, the mixing ratio, the N, number concentration, and Z, the reflectivity, into hail. And that deconvert is determined by the wet growth diameter. So I actually do a little iteration inside the model to find the wet growth diameter and limit it to a certain range, 5 to 15 millimeters or so, and then put that mass into hail. And for the 3 moment, you can just do that directly because the shape parameter adjusts to represent that, that set of values. In the 2 moment, we have to be a little more careful because if we just throw number and mass into a category with a fixed size, a fixed shape, then we can end up with weird or unrealistic reflectivities. So I use the reflectivity to adjust what the actual number concentration is that goes into hail. And I had an update to this in the current version of the NSSL scheme in WRF, but there's going to be an important update in 481 that does a better job, is more robust and doesn't have some occasional weird values. So the graphic I showed in the title slide is of one of my favorite storms. And this is an example I use a lot. It's from 2004 during a field program. And this was a beastly isolated supercell that went almost all the way across. Whoops, shoot. I just spilled some water here, sorry. Went almost all the way across the state of Oklahoma and remained isolated pretty much the whole time, and had crazy lightning, multiple tornadoes, large hail. Oh, thank you. There's a power strip up here. Pardon my mess. And these are some images of radar analysis from Kristen Calhoun, formerly Kuhlman, of this storm. And one thing I want to point out is this high reflectivity vault in the bounded weak echo region in here. And you just have this large area of high reflectivity. And so the question is, can you do that with a single large ice category? And I'm going to try to convince you that no, you can't. And then these are a couple more images from that paper. And I just want to point out the long forward flank region here with high reflectivity, the characteristic of the storm. I think we're stuck again. Okay. Lots of colors. All right. So thank you very much. So I'll just cut to the chase. So this is with turning off the hail category using 3-moment grapple, density prediction. I would think this is my best shot of trying to reproduce the storm. So on the left is the low-level reflectivity. It doesn't look terrible, but it doesn't look great. And then if you look at a vertical cross-section, oh, it's really weak up here. Because we have horrendous updrafts, 70 meters per second. They're just blowing things upward. The grapple fall speeds aren't large enough to fall against that and grow into hail. And yeah, this is just another view of that. Look at the dual polarization emulation. It doesn't look great. We do have a reasonable ZDR signature for and supercells we get what we call the ZDR arc. But there's no indication of hail in the correlation coefficient. And we have very low hail diameters, very low accumulation, almost no solid water accumulation at the surface. So now we turn the hail on. It's a very different story. We have a very well-defined high reflectivity forward flank. We have good high reflectivity upstairs. We get a good weak echo region. Down at the surface, we have a nice ZDR arc signature. We have reduced ZDR where there's hail falling out, and where we have the hail, we also have the low correlation coefficient. And we also get much larger hail sizes at the surface, up to 3.5 centimeters, and we get actual accumulations of hail at the surface. Which comes back into what happens when you're doing 2-moment. Early on I mentioned that sedimentation is an issue, and it's kind of the Achilles heel of 2-moment schemes. It's inherently problematic because of the way it's defined. There's a shock that develops, and this Wacker and Seifert paper illustrates that. And there have been a couple ways to try to deal with this. One is to just, let's just set a limit on the size of the particles. I'll show you how well that works. Milbert and Yao diagnosed a shape parameter. It works all right in pure sedimentation, but when you put it into a real situation with shear and melting and processes, it's a different story, but I'm not going to talk about that. You can also, instead of having the number concentration fall at the number weighted speed, you can boost that a little bit, and that reduces your size sorting, but also helps mitigate the excessive sorting. And the solution I came up with was to make it a quasi 3-moment scheme and do a correction after the sedimentation. And that prevents the reflectivity from growing, which is how I defined excessive sorting, is when you have an increase in reflectivity. And here on the left, this is a pure sedimentation of ice. What should happen is what's in like a bin model. You're looking at your reflectivity over time. As the stuff falls out, the reflectivity should not increase. In fact, it should slightly decrease. If you do a very simple kind of limitation, it doesn't necessarily work well. And with the adapted scheme, it actually does a pretty good job compared to the 3-moment. So here's another simulation of my favorite storm. And just looking at this, would you want to go chase it? Does it look like a good storm? Heck yeah. That looks great. I mean, he's got this big forward flank, you got this nice wrap up, but start looking a little closer. and we're going to find some warts on this. So here's that surface look again, but when we look at a vertical slice, we see strong evidence of excessive sorting. Here in the updraft and in the forward flank, you really got to move this thing around. So in the forward flank, all of this reflectivity is coming from excessive sorting. And in the updraft, we have excessive sorting because it's being floated there, and so it can't get ahead. And we have weird-looking ZDR. It has large hail all the way along the front or forward flank. And it's not good. And then this is another version of a simple limiter. Same story, except that if you're limiting the slope instead of the intercept, you get a different funny result in the ZDR. You have this flat ZDR, and then in both cases, we're not getting any hail to the ground, at least not any appreciable. And then if we do it with the adaptive sorting, it looks like that 3-moment grapple-only scheme that I showed before, which is good. Well, good in that it matches, but not good in the way it looks in the result. So same story, although we have a decent ZDR arc here, but there's really no hail signature, and this is a big hail-producing storm. So I talked about dual pole, that you need multi-moment to have reasonable dual pole results, and this is from some earlier work with Dan Dawson and a different storm. We're just showing how we got pretty decent looking signatures for supercell storms. And again, we have reduced ZDR in the hail region, nice ZDR arc. I don't know a whole lot about KDP, but I think that's okay. And the ρHV, the correlation coefficient, also represents the hail well here. And I like to use supercell storms because they're kind of the worst case scenario for size sorting. You have strong shear, which also induces sorting, and you're really going to see these things show up. If you're looking at more ordinary convection, you won't see as much evidence of the size sorting. So it can be okay in some cases. And then regarding real-time forecasts, I mentioned Warnham forecast, and this is from a few years ago, just showing 2 years of forecasts, and with 2 different microphysics schemes. And with the NSSL scheme, we had better object placement. And when I say object, I mean reflectivity object, I think greater than 40 dBz, and how far it was off from MRMS, the observations. UH was a little bit similar, but that's... Yeah. And I think that's all I have to show. Just to summarize, it's really aimed at as a research scheme, the NSSL scheme that is, but it has sufficient efficiency that it's not too much of a sluggard. The variable density provides fall speed diversity. How much that really impacts things, I haven't really looked into, but it sounds nice, doesn't it? And a key feature is the hail species. If you're doing severe convection, hailstorms, supercell storms, to get those more realistic dual pole signatures that suggest that the scheme is doing kind of the right thing. And if you're into aerosol sensitivity, you can use this scheme as well. It's compatible with WRF-Chem. And if you run a 2-moment instead of 3-moment is definitely more expensive, but not unreasonably more expensive than the 2-moment. And the next major version of MPAS 8.5 should have this and more physics that we're talking about today. And then, again, to repeat, if you're using the scheme currently in WRF, look for that 481 update if you're interested in the hail. And also there's a correction for the 3 moment that's less severe. That's all. Thanks.
All right, questions for Ted? We'll start with George.
I'm just coming from the chemistry guys over there. We had a meeting over there with MPAS, ChemPAS, and CAD-Chem, and all those different versions of the model. Now, your scheme is probably more focused on the severe weather, I assume, but you mentioned WoFChem, so that makes me ask this question. Anders has spent quite a bit of time to make sure the wet scavenging is done much more consistently inside the microphysics scheme. Have you thought at all about wet scavenging of aerosols in there, or you just leave that out?
Well, what I did to make it compatible with WRF-Chem was look at what other schemes had done and just copied that. So I haven't actually worked a lot with WRF-Chem to know what's going on, but it does, and I'm supposed to submit some updates to the documentation to say, oh yeah, and you can use the NSSL scheme too, but I haven't gotten around to that. So it's not really in the documentation. So the answer to your question is, no, I haven't.
Because the way WRF-Chem does the large-scale wet deposition, that's a really bad routine that I originally wrote, actually. And you can only invoke it by setting the nameless parameter to -10. So that tells you already you don't really want to use it. So it's much better approach what Anders has been doing, but if that's possibility with your scheme. Obviously, I don't think it's going to matter a lot for severe weather, but for folks interested in chemistry and aerosol applications, it does matter.
Yeah, well, things like that tend to get addressed when someone sends me an email and says, hey, I'm using your scheme and this is looking weird and can you tell me what's going on? And then I say, oh, well, maybe there's a bug in there. Or maybe it just needs, or something needs to be improved. But
you can always push it on that large-scale wet deposition.
yeah, all I know is that I think it has just, there's a wet scavenging term that comes into the microphysics and you put some values into it and it goes back out and the scheme doesn't know about it. But it does use the WRF-Chem droplet activation. So it changes how it does that. So there's an internal droplet activation because they have the predicted aerosol or CCN.
George, could you go back to the microphone?
Not that important of a comment, though. I mean, I think that's also the approach that's used by Morrison, with Steve Gann's approach with the activation.
It's different, although there is a, yeah, no, it's more what I detailed in my paper.
Doesn't
it's
matter.
a
It's a better
TUMI
approach
activation.
than the regular large-scale.
Okay.
Hi, Ted. Thank you for your interesting and informative talk. So I have a question. So you showed the simulation result of this supercell experiment case. Then I wonder that when we simulate some real case using the various configuration of physics schemes, do you have some recommendation to see the best performance of your microphysics scheme with the other PBL or the Cumulus or the other physics configuration suit?
No, all I can point you to is what configurations have been used in the Warren forecast, the WRF-based Warren forecast system. And it actually has an ensemble with 3 different PBL schemes for physics diversity to help the ensemble members be more diverse. And it seems to work fine with all of them. There's nothing that blows up, as far as I know.
I think it's good to know it works well with kind of all the physics configuration, right?
As far as I know.
Okay, thank you.
All right, let's take Ted once again. So now we have a 10-minute coffee break. We'll reconvene here at 2:20 p.m. Mountain Time for the next two of our talks. All right. Thanks, everybody, for coming back from our coffee break. 10 minutes is great to have a nice little break, but I know seeing everybody for the first time, it can be easy to get caught up. So with that, we'll go ahead and move on to our next two talks, the first of which is to be given here by Joe Olson on the MYNN-EDMF scheme as it relates to boundary layer and turbulence modeling. I've moved the timer here, Joe, and for Anders and Corey later on, so you'll have the timer right here even as the yellow can't really be seen.
Okay. All right. Well, thanks. I would like to thank my co-authors for all their conversation on both the design as well as the testing of the scheme over the years, and apologize for not giving them a copy of this talk for them to look at before I give it. Oh, can we get this in? Yes, sir. No worries. Okay, so I'm going to give a little bit of turbulence parameterization basics, because I get asked a lot of questions on pretty basic concepts. And most of these relate to, the different components I'll be talking to later in the talk pertaining to the MYNN-EDMF design. And if time permits, I'll go into a little bit of the status, availability, and guidelines for practical use. Okay, so I get this question actually more than you probably believe, but do PBL schemes perform mixing throughout the entire atmosphere? Most of you probably know this, but yes, the answer is yes. They do handle at all levels, inside clouds, outside clouds, whatever. We do tend to use the term PBL scheme, boundary layer scheme, turbulence scheme interchangeably, but really it's PBL scheme is kind of a misnomer. It really should be turbulence scheme. But nevertheless, we are charged with doing the turbulence everywhere. PBL schemes must represent distinct nature of mixing in various regimes if they're really to be good schemes. I mean, stable, unstable, cloudy, marine, whatever. And this requires like a mix of local and non-local approaches typically. And I'll talk about the different non-local and local approaches in the MYNN specifically, but I do want to add one thing here that I don't think exists much in the literature. If you read the literature, it's the scheme's local, the scheme's non-local. It's never that black and white when it comes to mesoscale schemes. They're actually, you should look at it more of like a spectrum, basically. Even MYJ is always considered a local scheme, but it has some non-locality built into the mixing links, for example. So it's partially non-local, actually. That should be taken into account. The only pure local schemes are the LES, and so when we design scale-aware schemes, they have to transform to be purely local. When you run at high res, but we need non-locality for mesoscales. Oops, sorry, I had one more bullet, and it's actually a really important bullet. I think PBL schemes communicate the surface heat, moisture, and momentum fluxes to the atmosphere via the lower boundary conditions. So basically, like the heat flux from the LSM is going to come into the boundary layer scheme, and it's going to end up being part of the boundary layer tendencies. And a lot of people, when they're trying to figure out where their biases are coming from in the model, they'll look at the tendencies and say, the boundary layer scheme is too warm. Well, it takes into account heating and other sources coming from other schemes, so it's never that easy to riddle out. I just want to make sure everybody is aware of that when they do their research, because that's very important. It's too easy to point your fingers at the boundary layer scheme for all the problems. Okay, what is a moist turbulent parameterization? A lot of schemes consider or categorize themselves as has been categorized as moist turbulent schemes. Well, a boundary layer scheme, I think, can be considered moist turbulent if it uses information or cloud information to regulate the turbulent mixing and directly impacts the cloud morphology. Could even be by just simply mixing the cloud species or whatever. But the actual degree of the cloud turbulence coupling can vary significantly between different moist turbulent mixing schemes, since there really is no standard classification. So, for example, I think some of the older schemes who get it over there. Okay, so some of the older schemes just basically mix moist thermodynamic variables and mix the clouds, and they kind of categorized it as a moist turbulent scheme. But you can go much further than that. You can add features like non-local mixing from cloud top radiative cooling, estimating your own subgrid clouds within the scheme, and have that directly impact the turbulence. You can have updrafts and downdrafts with some microphysical processes like latent heat release and evaporative cooling, which directly impact the turbulence, and so on. I would say that the MYNN basically sits in this category right now, and we're working on making what I'd consider to be more fully moist turbulent by bringing the same microphysics that's in the full microphysics scheme within our subgrid clouds. And by doing this, we're doing this prognostic cloud extension of tempo that Anders will kind of mention later on. But it's not fully public yet. It's still under testing. Okay, so there's a variety of scales of turbulence, and going from just local mixing to some non-locality and shallow cumulus to deep cumulus, like in George's world. I think the MYNN looks at this spectrum right here. It takes into account the local mixing and plus some non-local mixing associated with top-down radiative cooling and shallow cumulus. So basically, if I was going to give a very high-level overview of the MYNN, I would say that it's a moist turbulent multi-closure level scheme with integrated spectral updraft and downdraft mass flux components to represent the non-local mixing. It also has the ability to create or to specify its own subgrid clouds, both stratus type subgrid clouds and convective subgrid clouds. So let me talk about a few of these components here, starting with the local eddy diffusivity portion of the scheme, which is the first term right here in the total turbulent flux equation. So it's basically, just run at level 2.5. It's just a TKE-based scheme, but it has these options I'll get to later. I would say that, I'll get to some of this later, but it's basically, it's an EL type scheme, meaning it's a TKE mixing length type scheme. It's got a little bit shifted on me, but the eddy viscosity and eddy diffusivity are defined as the mixing lengths, Q, which is twice the TKE, square root of that, and the stability function. So I will overview some of these components on the next few slides. The different closures spanning between 2.5 and 2.7, they're basically controlled by this closure name list option. 2.5 just gives you a TKE. I added the 2.6 just to get a better continuously evolving Q prime squared, to get overall better behavior to feed into the cloud PDF, since Q prime squared is, of all the higher order moments in my experience, is the most important for the cloud PDFs. When you run a level 2.7, you can make this a total turbulent energy scheme, because theta prime squared is a good proxy for total potential energy. And so that's my TTE closure. And then the full level 3 scheme gives you the covariance. And that originally came with its own counter gradient method for non-local fluxes, but I think it's actually easy to beat with the mass flux scheme. So if you run it with the mass flux scheme on it, it kind of overwrites that counter gradient method. So we really should run with one or the other only. Here's one simple example of the total turbulence energy closure. This is taken from an old RAP case. If you look at this cross section just off the shore of Oregon and California, this stratocumulus area, you can see the PBL height is this dashed line here, and you can see the strong turbulent or strong stratification above that, and the clouds, aligned with it. The TKE is below it, where the stratification is less, basically. The TPE is up in that stratified region where the TKE is consumed and producing TPE, so the total turbulent energy is a combination of the two. And that just basically allows for a little bit of mixing in that layer, is ultimately what it does. But the stability functions become so small in that highly stratified layer that it doesn't allow much for mixing. It allows a little bit of momentum mixing, but heat is basically shut off at that point. The differences in overall behavior between that and the 2.6 aren't that impressive. They're pretty small, actually. If you look at the TK equation on the face of it, it looks very similar to other TK equations. It has a vertical transport term where the turbulence kind of transports itself as a production of shear, buoyancy, and dissipation. For that vertical transport term, it has its own stability function for TKE, which is set to 3 times the momentum stability function, which is tuned by Dr. Nakanishi to LES. The TK can be transported in the mass flux components, but in my opinion, the differences are small enough where it can be neglected. So I have this by default set to 0, this option. But the buoyancy production of TK does include automatically TK source terms from both the updrafts and downdrafts. So there is that connectivity between the local and non-local components. All the TKE is turned into heat according to this equation. This doesn't affect a normal boundary layer that much, but it does have a significant impact in hurricanes. Okay, so the performance of TKE is verified a few times in the literature, and this one in particular by Josh Wadler et al. He did 2 simulations here, one of a Cat 1 storm and a Cat 5 using the MYNN, and measuring that against P3 data and Coyote data. And you can see it's always in the ballpark, basically, except for we don't have any data. We don't know what's happening really in this Cat 5 situation. And other places like this Alaskan coastal barrier jet, this is actually one of the first simulations ever done with the MYNN, I think back in version 2.9, before it was implemented in 3.0. You can see it has this elevated maximum away from the surface that the MYJ couldn't get, and that kind of shows up in our data there. So I think, in general, you can expect the TKE, performance to vary in different regimes. But now that it's more well coupled to the non-local components of the scheme, I think it's more generalized. And it should perform better in a wider variety of environments. I don't consider this particular aspect of the model to be high priority for future development, but that said, we have recently done some tuning on it to improve our low-level jets in the WFIP3 framework. You can see for Block Island here, just off the coast of Long Island and Rhode Island, I'm showing here some time height profiles of wind speed. This is from the window E observations where it blends radar wind profilers up high with LIDARs down low and surface met data to get one continuous profile of observations. older version of MYNN was clearly too diffusive, and the updated version gets the jet a lot better. I think it's still a little bit too weak, but it at least halved our biases so far. Here's another case in July of the following year where it also performed much better. We have a lot of good results for improved low-level jets now. And it also, this work helped improve, 10-meter winds over CONUS as well. We'll move on to the non-local portion of the MYNN. And, the spectral mass flux scheme transports all these variables by doing a variety of different plumes of different widths. Each plume is integrated up in the same way using the Simpson-Wiggert formula, but as entrainment rates differ that are inversely proportional to the vertical velocity and the width of the plume. So these smaller plumes basically are going to be weaker because they're going to have larger entrainment, right? So they're usually just performing non-local mixing within the boundary layer. And the wider plumes, pierce the boundary layer and produce some entrainment mixing on the top of it and can go higher and produce clouds. This is an example of how it changes in behavior over the time of the day. This is on the left, you have the maximum plume width, and you can see how it grows as the sun comes up, and it's pretty much saturated at about 1 kilometer midday, and then it decays away. On the right side, it's mislabeled. This is not liquid water path. This is actually maximum mass flux in the column. And so this is, and the mass flux is always positive. I just, for the sake of this plotting, made it negative if none of the 8 plumes are condensing. So it's a clear sky or clear boundary layer. If it's red, it's condensing. So you can see there's a cyclone here with a front coming down here. Behind this cold front, you can see there's a lot of condensing plumes midday, and on the edge of this region too. And this basically the shallow cumulus fields, verify quite well. I think they're one of the best features of the MYNN, in my opinion. You can see in the GOES imagery, there's a lot of shallow Q in this area, and flanking these thicker clouds down here behind the front as well. The simulation largely shows the same thing overall. And if you take a cross-section from this clear sky area to this overcast area closer to the coast on the right, you can kind of get an idea what the scheme is doing. Here, I'm plotting the mass flux in the column. And again, I'm colored it differently when there's no condensation in it. So you can tell I'm creating shallow cumulus clouds over here, but not over here. But that's the point of it. I mean, that's what I think the benefit of the EDMF framework is that the mass flux scheme can, it tries to create tries to capture the depiction of the plumes that are plausible in a given environment, basically. And by doing so, it has some component that's slightly piercing the PBL height here, which is in this dashed line, creating some of that entrainment at the top of the boundary layer. But when it's too dry, it's not going to produce shallow cumulus clouds. So more moisture, closer to the coast. It's all of a sudden the level, the LCL is basically lower than the PBL height over here. These plumes are condensing below the PBL height. And then you're getting that secondary maximum in mass flux that's commonly seen in shallow cumulus environments. So you get the clouds reasonably well depicted, that cross PBL height fluxes in both scenarios, cloudy and clear. Here's some example of how it performs for a variety of different shallow cumulus cases. These are 10 cases taken from the 2018 LASSO set. This work was originally started by Wayne Angevine and is carried forward by Man Zhang. And so what I'm showing here basically is on the left is some LES for this. And these are time heights again for the cloud liquid water. And I'm comparing this against GFS version 7. This is a prototype, not the final version here. And against the RAP suite, which has the MYNN in it for these 10 cases. I do want to point out, though, that we're comparing in-cloud mixing ratios versus grid means here. So if you multiply this by the cloud fraction, it wouldn't look so top-heavy. It would look more like this. But this is still a good comparison for showing the onset, cessation, the cloud base and cloud heights. You can see how it evolves. And I think not all these cases are flattering, but I think in every single one of them, the MYNN is kind of in the ballpark at least, you know. And so I think it shows that it is flexibly robust to do shallow cumulus problem. Moving on to the downdraft non-locality, we have a 5 downdraft plume. In this model, it's effectively the updrafts turned upside down, more or less. But the bottom, or the smallest plume is a width of 100 meters. And the largest one can be a maximum of 500, but it almost never achieves that width. It's usually more like around 300 or 300, which compares well with LES observations of these, coherent structures in stratocumulus that tend to be more like around 200 or 300 meters of downdrafts. It's that the width is primarily a function of your net radiative cooling at the top of the cloud, but it's also a function of the grid spacing to make it scale aware and the height of the cloud, because obviously if you get a stratocumulus that's very shallow, or even fog case, you're not going to have like a 500-meter plume descending from that fog top, right? So it's tapered in a few different ways. In that case, for fog, actually, the mass flux portion is actually shut off, and you just get a vertical profile of the TKE in that shallow layer, just to help promote the local mixing. The entrainment rates are the same. The activation has to be greater than 8 degrees Kelvin per day of cooling, and a 50% cloud fraction. I'll show you an example of how this works, actually. Here is a loop of the cloud top cooling at the, diagnosed in the model. So you can see at nighttime, cloud top cooling is larger. During the daytime, when the solar radiation starts to cancel out some of the long-wave radiative cooling, you can see the cooling drops quite a bit. When it does that, the maximum width of the downdraft, it's large, up to 350 or so at night, but it shrinks more like down to 200, 250 during the nighttime. So it has a pronounced diurnal cycle, as it should, because the forcing has a pronounced diurnal cycle, and that basically weakens the downdrafts considerably. Meanwhile, at the poles, there's much less of a diurnal cycle, so it has a little bit more of a constant behavior. Due to time, I'm going to move on to representation of subgrid clouds, and this is just going to focus on the stratus component. This BL-MYNN cloud PDF option is what controls which option you want to create your subgrid clouds. In the past few years, this option number 2 is the only one that's really changed. It's because now with the level 2.6 and 2.7, we've fully used the Q prime squared that's diagnosed to basically parameterize the standard deviation of your saturation deficit. The Q1, which is the normalized saturation deficit, is the main variable that goes into these cloud fraction functions, basically. And what's new here is we're having a little bit too much of a patchy fog problem in older versions of the MYNN, so we have a different cloud fraction curve within the boundary layer that blends to one that is more valid above the boundary layer. And then we figure out our cloud mixing ratios like so. And basically this alone has helped improve some of our high cloud bias over water, but only where there's subgrid clouds. You could still have some resolve scale clouds, and this of course won't help that. So you can specify your subgrid clouds, but how do they connect to the turbulence? Well, they connect to the turbulence because you basically calculate an effective static stability. And now this option didn't exist in previous versions of the MYNN because it just defaulted to this. It's now option 0. It just used the buoyancy flux functions from the Samaria-Deerdorf 1977, and which worked on the subgrid clouds you got from any of the cloud PDF options. And it worked fairly well. It was tuned up to work the best it can. I added this new option from O'Gorman. It basically destabilizes the lapse rates a little bit in any grid cell where there's a little bit of turbulence and subgrid clouds by adding a negative adjustment that's proportional to the vertical gradient of the saturated equivalent potential temperature, which is mostly unstable in the tropics. So if you don't use some type of parameterization for effective static stability and just use the dry static stability, really what's in the tropics doesn't vary that much compared to what's in the mid-latitudes. You're not going to get that much of a difference in your turbulence. But when you take this into account, the effective static stability can drop significantly and even become on the order of, say, 25% of what the dry static stability is in the tropical boundary layer. So this helps out in some areas, giving us a little bit better of a PBL height. After all the work we did to make the scheme more stable and work better for low-level jets in the mid-latitudes, we needed something that would help it, be a little bit more active in the tropics, and this helped out a little bit. And it's just a few examples of how it performs in the tropics. A while back we did a handful of simulations from the atomic Eureka campaign. Basically, this is just one example of where there's a lot of different types of clouds, like these sugar clouds, so to speak, in here, these flowers, which are these, organized shallow cumulus, and that transition between the smaller scale shallow cumulus and the flowers. And then when you get a trough digging down into the tropics, you get these so-called fish clouds, and we can overall get those too. These are the model simulations at 3 and 12 kilometers, and this red square is the approximate area. They don't perfectly align with the satellite imagery. But if we look at a cross-section to look at this transition of small-scale clouds into organized flowers, which ends at this circle that they flew planes around and dropped a bunch of dropsons. We'll compare those profiles later, but looking at this cross-section first, you can see that overall, both 3 and 12 kilometers, you get this transition pretty well with the smaller scale shallow Q. Even at coarse resolution, it's done reasonably well. We start getting the deeper organized flowers to the left of this, and as a rule of thumb in the tropics and the trade wind areas, like when the cloud depths get greater than 1 or 1.5 kilometers, they can even start to precipitate, and we can see some of that as well too. So I think we're doing okay with a lot of these cases. This is just one example, but every single case we looked at, our model profiles at both 3 and 12 kilometers actually, fit the profiles pretty well. These are 42-hour forecasts, so it's not that long, but long enough for the clouds to spin up and to say they're truly, our MYNN clouds, so to speak. But you can see we're getting a thermal stratification up through the trade wind inversion. The RH is definitely in the middle of the pack with all the drops-ons. Doing pretty good for momentum too, but we're still missing some of these large variations in the free atmosphere, so I don't know exactly what they're coming from, if they're upper level cloud errors or what. So status and availability. We do have the MYNN now available in a standalone repository. It's in NCAR space. We have this hooked up now to WRF ARW, and we got hooked up to MPAS. We think it'll be in version 8.5, but I haven't been briefed otherwise. We're going to try to get it to CCPP next. We have updated documentation for this that just came out earlier this year. We'll note that not all, with each of these implementations, each one has their own driver that connects to the host model. I'm trying to change that. I'm trying to sync that as I work on the CCPP update. And we now have automated CI testing too, so it's going to be much harder to bring bugs into the host model. I want to thank Shia Sun for getting that set up, and Jimmy Dudia for being my advocate or collaborator on this, because it is in NCAR space for reasons that we probably don't need to talk about. But it's the case. I needed Jimmy to give me the okay on that. Anyway, it's not GPUized yet, but I think that's upcoming. I think if I'm going to say anything about guidelines for practical use, I think the biggest thing I worry about is like whether or not you want to run with a standalone shallow cumulus scheme or run with the mass flux scheme in MYNN. Now, the MYNN is always tuned and designed to run with that mass flux scheme on, because that's the source of its entrainment. I know some people don't run with it on. If you want to run with your own shallow cumulus scheme, there's going to be double counting. There's almost nothing you can do about it. So I'd suggest turning it off then if you really want to run with another scheme. But keep in mind that you're definitely going to lose some of the entrainment, certainly in the dry. May lose all the entrainment. I don't run it in that mode, so I don't suggest doing that, but I know some people do. Don't use the mixed total water option. It will mix clouds by default. By default, this is set to 0, which means it'll mix all the separate species separately. Whereas this, it's frozen now. It's on. Heads up. Second to last slide anyway, so we can deal with it.
Joe, if you want to have time for a question or two, we should probably wrap up.
Yeah, this is basically the last slide. It's only the summary slide left, and that's going to tell you nothing what I didn't already tell you.
All right, well, let's thank Joe. We have time for a question. Lou?
Joe, I have a question that I'm sure you've thought of, or at least been talked to about. Is there an opportunity, we're moving towards not like WoFSCast is now not just trying to go away from the multi-physics for the PBL. Is there an opportunity to have a discussion or something where we may be able to use multiple, like obviously there's variation in how you set parameters in the model, and it would seem to me that having some set of variable settings, if you will, that get slightly different answers might be very useful for the ensemble data simulation. Do you have any thoughts on that?
Yeah, actually, Anders and I have talked about this a lot. So there are a lot of options with the MYNN, so you can set it up a variety of different ways, and even with and without the mass flux scheme if you want, but the different cloud PDFs, the different mixing length options, so on. You can set it up. It might not be a massive ensemble spread. It's also hooked up to SPP, this stochastic parameter perturbation, so you get more spread through that. And Anders has a lot of options in tempo too, and so I think there's a way we could set it up to get a lot of, well, at least get halfway there with just our, configuring of our schemes.
Right. if it's really quick.
Yeah, it's very quick. So you said the low-level jets are quite well represented over the SGPs. So did you get a chance to check some of the low-level jets in the Asias or Africas or South Americas? How does they compare with the SGP?
I have not. Yeah. I would love to, though.
All right, let's thank Joe once again. All right, next up is Anders Jensen, also from the Global Systems Lab, to talk about the Thompson-Eidhammer Microphysics Parameterization for Operations, or TEMPO. Anders, all yours.
Thank you, Clark. Which one of these is the... All right, so I'm going to be talking about TEMPO. It's kind of a mouthful, but it's easier to say TEMPO than Thompson-Eidhammer Microphysics Parameterization for Operations. So we named it TEMPO. TEMPO also lives in in-car space, so there's a link to the TEMPO repository and a link to the current TEMPO documentation. TEMPO is obviously based on the Thompson-Eidhammer microphysics scheme, so it's a bulk microphysics scheme, and it's mostly developed for NOAA operational usage, but it also can be used as research applications. All right, so just kind of a quick summary of what we are trying to predict when we run a microphysics scheme. So the figure on the left shows a real cloud, and this is what's going on in a real cloud. You have warm rain processes activating cloud drops, getting converted into raindrops. Further up, you have ice processes, so you're nucleating ice, you're growing snow by vapor deposition. You are riming some of those snow particles if you have super cold liquid, and then the very top of the clouds generally just have cloud ice. So all of these processes is what we're trying to represent when we run a microphysics code. And, Ted talked about this a little bit, but when we run, a traditional microphysics scheme, we kind of break things down into these categories based on properties. So you have things like cloud water, or the small cloud drops. You have raindrops, which are larger liquid drops. Snow, which is just vapor-grown or aggregated ice, and then grapple, which is rimed ice that can turn into what is grapple and or hail. So for the TEMPO bulk scheme, again, as a bulk scheme, we're predicting the microphysical processes that are occurring in clouds, and also the evolution of various properties such as mass and number mixing ratios for various hydrometeor categories. Being a bulk scheme, we don't predict and track every snowflake in a grid volume. We assume that there's some distribution of those particles, and we track the distribution, which keeps things much more computationally efficient and mathematically easy. So TEMPO does include various levels of details. This is kind of similar to the NSSL scheme. So you can run this with various levels of details for these different categories, such as cloud water, rain, cloud ice, snow, and grapple. I don't think, okay, these will pop up now. So basically, you can run this with one moment cloud, kind of like the original version of the Thompson scheme. But kind of the more recent options that were added are the aerosol-aware version. That's the Thompson-Eidhammer version from 2014. That includes the double moment cloud water and the prognostic water and ice-friendly aerosols. So when you run with the aerosol-aware scheme, you have those three added prognostic variables. And then more recently, there's the hail-aware version, which includes a double moment grapple parameterization with predicted density. So that includes two additional variables in blue, grapple number concentration and the grapple volume mixing ratio, which gives you the density. Again, the more details you add, the more expensive the scheme is going to be, but I'm going to try to convince you that you should be using all of these schemes when you run this tempo, as we do in our testing. And just kind of a quick point that when microphysical processes and diagnostics, things like reflectivity, drop sizes, snowflake size, they depend on all these properties, mass, number, volume. So when you predict more properties, you get more accurate, reflectivity and particle sizes. So for the rest of this talk, I'm going to kind of talk about some of the options that are available in MPAS and WRF, specifically that aerosol-aware and hail-aware option that we're currently testing with for our research runs. I'll talk about some current development. I'll talk a little bit about improvements to the aerosol emissions that we're working on for the aerosol-aware scheme. I'll talk about some modifications to grapple and hail for deep convection that's based on a lot of the work that Ted has been doing. And then I'll talk about some improvements to the coupling to the MYNN and subgrid scale clouds. So there's a couple of things that we're working on that front. One, trying to make the subgrid scale and the resolved clouds more consistent with the radiative properties. And another thing we're working on is a prognostic cloud fraction scheme that Joe mentioned. And then finally, I'll give some details on the tempo, the repository, a little bit of a code overview, and how to use this scheme with both MPAS and WRF. Okay, so with the aerosol-aware option, you do have the 3 added variables: cloud droplet number concentrations, water and ice-friendly aerosols. And when you use this version, when you turn on this option, the aerosols control the number concentrations for both cloud droplets and ice. And so this affects, a lot of different things, from your cloud lifetime, your drizzle production, your rhyming rates, ice nucleation, as well as your effective radii for your cloud and ice, which go into the radiation calculations. So generally, when you use this has been actually used in the HER model for a while. It results in general improvements kind of to the whole aerosol cloud precipitation radiation coupling. We see improvements to precipitation with this. We see good prediction of things like super cold liquid water and super cold large drops in clouds. So it's very recommended to use this option, to continue using this option. The figure on the right is from the original Thompson-Eidhammer paper, just showing that when you do use a 2-moment cloud water, you do get a kind of a distribution of drop sizes as a function of water content. So you get a lot of variability. All those colored points are different drop sizes based on different water contents from a WRF simulation. And when you don't use this, when you just have 1-moment cloud water, you get those single lines of drop size as a function of water content. So, and it obviously depends on what you select as a number concentration if you're using this 1-moment version. And so your clouds and all your processes are going to be very sensitive to this. I mentioned some work in progress. Basically for this, see Hai Chin's talk tomorrow. He'll go into more details, and George mentioned this too. He'll go into more details on improvements to our aerosols for this parameterization. So we're working on switching the initial condition from go-kart to Mera and actually having real emissions come into the scheme. So emissions of things like sea salt and dust. Whereas now, currently, the emissions are just based on the background climatology. They are highly tuned at this point. We do have them tuned up in a way where we think provides good, reasonable forecasts over maybe a 24 to 48 hour period. But again, Hai Chin is working on making this a lot better. So don't miss that talk tomorrow. In terms of the hail-aware option, this adds 2 additional variables: the grapple number concentration and the volume mixing ratio, which is needed for density prediction. Ted covered this in his talk, but these have, pretty big control over the Grapple hail size and fall speeds. In tempo, Grapple hail is just one category, and that's done for computational efficiency, so there's no explicit hail category. But when you use this, the hail aware option, you'll get Grapple densities that vary as a function of what's going on in the clouds. So if you have deep convection, you'll get higher densities, more hail-like particles. If you have light riming, you'll end up with lower density particles, kind of away from convective updraft cores. And if you don't use this option, if you just use the original one moment Grapple parameterization, you'll have constant Grapple density everywhere in your domain. Now, this does produce a lot of changes when you have Grapple hail number and density prediction. A lot of the changes come through changes to the size of those particles when you predict the number concentration, as well as changes to the fall speed when you have density prediction. So we do see a lot of changes to things like reflectivity, precipitation at the surface, especially frozen precip. But we are seeing really good results from a lot of the diagnostics that we look at, including hail sizes, reflectivity, and just reflectivity statistics over the course of like the spring forecast experiment. So I'll talk a little bit about kind of how we evaluate tempo and how we kind of guide our development. So at GSL, we are running tempo in 3 MPAS-based Rufus version 2 development systems. So we have, these are 3 kilometer over CONUS. We run about 20 runs a day with tempo microphysics, using both the aerosol and the hail-aware options turned on. And the figure on the right shows a performance diagram. I think this is like a year of data, and our MPAS simulations are in yellow here. So this is performance for different precipitation thresholds. And we have really good bias characteristics, using these options for, total precipitation compared to the HRR in red. So we're pretty happy with both of these, running tempo with both of these options in our systems right now. So we also are continually evaluating tempo in different test beds, such as the spring forecast experiment, the SFE, PAIR, which was an atmospheric river forecast experiment, and FFAIR is a flash flood precipitation experiment. So let's see here. So I'll talk a little bit about some overview results from this year. The figure here is the subjective scores from this year's spring forecast experiment, and this is basically how well do you like the looks of storms measurement. And MPAS, there's a couple of MPAS runs, and the HRR were the top performers for the for storm characteristics such as reflectivity. So this is a good sign that we're doing things decently correct. The figure on the left shows the bias characteristics across different reflectivity thresholds. And I'll point out a few different models. The HRR is in green, so the HRR model has a high bias if you get kind of larger than about 50 dBz. The version that we were running, our GSL MPAS version, again with both aerosol aware and hail aware options turned on, is in purple here. And the bias characteristics are pretty flat across the 30 to roughly 65 to 70 dBz range, but it is there is a little bit of a low bias across the spectrum, especially as you get kind of into that 50 to 55 dBz range. NSSL was running a version, and that's in kind of the yellow gold color there. And it actually has some better bias characteristics. It's shifted closer to 1, so, you know, close to our purple line, but shifted to closer to 1. So that's, you know, they had some changes to the Grapple-Hale fall speed in their version that I think are a positive impact that we are also working on getting into our back into the main tempo repository. So again, we're happy that our frequency bias is flat. We want it to be at 1, you know, across the dBz threshold. So that's what we're working on. We're working towards getting really good bias characteristics with the scheme. Okay, so I'll talk a little bit about some of the potential changes that we're working on. And again, this is very much motivated by Ted Mansell and work that he's been doing with improving fall speeds. So on the left, we have our control simulation. This was a day from April, storms across southern Oklahoma and Texas. On the right, we have a change that we're testing that includes some modifications to the Grapple fall speed. Again, this is a change that results in a reduction in Grapple fall speed aloft based on the air density. So it gives you these kind of fatter storms that we think are providing some of the better bias characteristics from the last slide. But this version also has some changes that kind of tilt the Grapple-Hale category more towards Hale, because when you reduce the fall speed of Grapple, you end up with you know, reduced precip, weaker cold pools, and so that change alone you know, resulted in weaker precipitation. So we had to kind of add some modifications to make Grapple-Hale more Hale-like in convective storms. So you know, to answer your question from before, Ted, you are slowly convincing me that, you know, maybe explicit Hale is a better way to go. But we're going to try to do it in a very computationally cheap way so that we can, you know, maintain this for operations. So I'll talk a little bit about how we're trying to improve coupling between the explicit clouds from Tempo and the subgrid scale clouds from the MYNN scheme. So if you're running with the aerosol aware scheme, Tempo predicts cloud mass and number concentrations. Those variables go into predicting or diagnosing a cloud effective radius for the radiative characteristics of these clouds. The subgrid scale clouds from the MYNN don't do this. They don't have number concentrations. So currently they use constant values of effective radius so that they can, you know, there can be a radiative impact from these clouds. These values are constant. They're different over water and land. So the simulation or the image on the left shows, if you look at cloud effective radius at 1 kilometer AGL, you'll notice, for example, over the ocean, you get these big decks of constant effective radius from subgrid scale clouds. So in order to, you know, better couple the MYNN and the Tempo microphysics, we developed a machine learning model so that we could provide subgrid scale clouds with a number concentration and then give them an effective radius that's consistent with the explicit clouds or the clouds predicted by Tempo microphysics. And that's shown in the middle panel. When you run with the ML scheme, you get your subgrid scale clouds now have variable effective radius coming straight out of this machine learning model. So we did some comparisons to observations at a couple of different locations, but I'll just show one at Columbia, Louisiana, the green star. So in the figure on the right, we have effective radius retrievals in gray. These were provided by Dave Turner at GSL. And when you run with the control simulation where the subgrid scale clouds have constant effective radius values, you'll notice that the scheme does pretty well at predicting the kind of the timing and location of these subgrid scale clouds, but they all have a constant value of effective radius. That line is pinned at 7.5 over land. So with the ML scheme, the orange plots, you know, we get obviously much better variability. We get better statistical comparisons to the observations. So this is a feature that we've been using now for a while in our real-time runs. The first quick look showed that we got some improvements to radiation, so we went with this, and we're continuing to use this ML model. I'll note that we're also applying, trying to use this for other methods. So all the cool kids are using machine learning, so we're going to do it too. Joe mentioned the prognostic cloud fraction scheme. This is very much a work in progress, but it's slowly converging on a solution that we'll be happy with and release to the public. So the basics of this scheme are that we're combining the explicit clouds from Tempo and the subgrid scale clouds from the MYNN scheme. There are a couple of added prognostic variables when you turn this on. So you have both liquid and cloud ice fractions being predicted and advected. So that's an added cost. And also there's a lot of changes to the microphysics scheme, because now not only does it have to bring in source terms from the MYNN, but it also has to be modified so that it only works on what is considered the cloudy portion of a grid cell. So, the cloud fraction kind of gets entrained into all of the microphysics processes. Again, this is a work in progress, but the figure on the lower right shows, kind of where we are. This is just a case from last May. This is, I think, a 18 or 19 hour forecast with the prognostic cloud fraction scheme turned on. So in this case, all of the subgrid scale clouds are running through the entire microphysics, so they're evolving like the explicit clouds would. Okay, so now I'll pivot a little bit and talk some about the Tempo repository and what we're doing with kind of the code management side, and then how to run the Tempo microphysics scheme. So we've gone to a single source repository. I guess getting rid of the multiverse, as George put it, of different Thompson-based schemes in different models. So we have a single source repository, and then MPAS, WRF, and the CCPP all point to the same code. We have different releases. So the current release is version 3.1.0. So we'll, these different versions can be tagged and cited as it's used, so we can kind of keep better track of who's using what, and which versions are being used for this and that. Code updates, releases, now they just kind of happen when they happen. So if we find a bug fix, we push it and we update the semantic versioning. So the suggestion is to always use the top of main if possible, because it's always going to have kind of the latest and greatest and all the bug fixes included. Tempo is broken down into, there's a few different folders in the repository. There's your standard workflow folder that does your CI testing. There's the main Tempo code. There's a tables folder that doesn't really have anything in it, because we decided not to put lookup tables in that folder because they are pretty large. So it's going to be pretty empty. Ignore that one for now. There's a test folder with unit tests and some program tests, documentation, and then there's a tools directory that contains code that you can use to build lookup tables. So the main, the source folder is, Tempo has been divided into these different modules. So there's a configuration module that contains configuration settings. In WRF and MPAS, these get overwritten in the code, but you could go in there and change them before you compile the code if you wanted to. Parameters are in the parameters file. We have utilities. We have an aerosol module that handles some of the aerosol related functions. There's a diagnostics module that handles all the diagnostics, such as reflectivity, precipitation, effective radius values. There's a tables module that provides code to calculate lookup tables. So the lookup tables are just offline calculations for different types of hydrometer collections that would otherwise be very expensive to calculate inline in the code. There's a machine learning module that handles the machine learning hookup, and then there's the main code, which is the main 1D microphysics, and the single unified driver, which handles initialization and the run procedures, and it's a unified driver for all the different models. So it's, it's the same driver for WRF and MPAS and CCPP. So if you're running this in MPAS or WRF, again, the driver contains the init and the run routines, or the run routine calls the tempo main, and the main tempo main has the main 1D column-based code. So I just have here a schematic of kind of the entry points from either WRF or MPAS, just for in case someone wants to look at this later. But there's both WRF and MPAS, they call tempo init one time for configuration settings and to calculate some constants, and then the drivers in each call tempo run. That goes into tempo main, which then handles, again, all of the stuff that's going on in clouds. So everything from the warm rain process, ice processes, aerosol processes, cloud condensation, sedimentation, and then a big update to everything and diagnostics, and then you're done and on to the next time step. So I wanted to have a slide on how your just kind of a workflow of the questions you need to ask and the user, the nameless settings you need. So, do you want to run tempo microphysics? The answer, I don't know, it just always points to yes. Do you have the lookup tables that include the offline calculations? If you don't have them, you can download them. You can ask me, I'll give them to you, tell you where to download them from. You can build them yourself from the executable in the tools directory. Same lookup tables for WRF or MPAS, so don't worry about it. You build them once for MPAS, they'll work for WRF. And then in terms of the model settings, if you're using MPAS, you want to set config micro P scheme to MP tempo. And then tempo has its own registry, since we have a lot of different options and features that we're working on. So there's a physics MP tempo block in the name list that hooks up to the tempo registry. And the default variables here are to use aerosol aware true and hail aware true. In WRF, it's MP physics 88. That's kind of based on the original Thompson, which was 8, and other versions, which were 28, 38, and then we skipped a bunch, and now we're at 88. You do need to set aerosol aware to 1 and hail aware to 1 because they are currently not set to that by default in WRF. So if you do use this, you need to set those to 1 by default. Okay, so this is just a quick sanity, basically a sanity check case, comparing tempo in WRF and MPAS to MRMS precip for an atmospheric river case from this past December. Really, the idea here is that if you're running the same version of tempo and MPAS with aerosol aware and hail aware options turned on, you're going to get very similar characteristics if you compare WRF to MPAS. And then on the left is the MRMS estimated. This is just a short 36-hour forecast and looking at 24-hour accumulated precipitation. But the idea is that, you should get very similar characteristics between these two dynamical cores. It's really hard pressed to find too many differences. They do exist if you kind of squint and stare at it for long enough, but you're going to get very similar characteristics if you run, again, the same microphysics scheme in these two models. And if you want to hear more about this case and some other atmospheric river cases, come to my talk in Madison for the AMS Madison Summit in August, and I'll talk about more of these cases. Okay, so this is just like a other things slide. This is like everything else I could kind of think about on what's going on. We've been working on a GPU version of Tempo. This is actually pretty close to being released. I know there's been a lot of work to incorporate GPU capabilities into MPAS, so this should be, close to being available. So we'll keep the community updated on that. We're also always working on new tests, both unit tests and feature tests, just to make sure that all of our options and stuff remain supported, and new code doesn't break old code. I've been asked a few times about a technical note, and it is in the works. It'll be like a 2026/7 time period, hopefully. But for now, there is pretty good documentation through GitHub. So, if you go to the GitHub page and look at something, look at a different function or procedure, there's lots of notes, there's links to papers, there's links to how things are done. So I try to keep really good documentation. So, if you have a question about the code, you can go, try to figure out what's being done. Yeah, and that's it, I think. Oh, that's counting up now. So 30 seconds past. Yeah, this is just going to show the current status of Tempo connected to, it's connected to a NOAA fork of MPAS. The 8.5 version, I think, is coming soon for NCAR's MPAS, and then it's connected to WRF, and then CCPP is still in pull request status, but it's pretty much done. So with that, thank you.
Yes, and as Anders notes, open to community development. I think there's even a little sticker you get if you do make a contribution. So we'll open up for questions over here.
Yeah, so you mentioned that NOAA is using it for a limited area, 3-kilometer CONUS experiment. Did you get a chance to have global or refined mesh, and how does that compare with the global version? And then the second question that I would have is, how does Tempo perform over complex terrain?
So for the first question, we are mostly in the process of trying to set up some tests of both global and variable resolution for kind of some different projects. I think we're going to be looking at variable resolution for atmospheric river cases in the near future. But hopefully maybe by next year I can present more on tests in global and variable resolution. For the complex terrain issue, we think it performs pretty well. I mean, kind of similar to how the Thompson scheme would perform. Like, for example, the case I showed for the atmospheric river event over Oregon, we get good precipitation prediction compared to like MRMS accumulated precip. So yeah, I mean, it performs pretty well. It's not perfect. There could be some issues to work on, but for now we're pretty happy with the performance.
Thank you.
Any further questions for Anders? All right, well, hearing none and seeing none online, we'll get you off the hot seat a little early then. Let's thank Anders once again. All right, we have another 10-minute coffee break here, so we'll reconvene at 3:43 Mountain, or just after, for our last talk of the session, where we shift gears a little bit from physics parameterizations to machine learning. All right, so welcome back to our fifth and final talk of this session, to be given by Corey Podfin from NSSL on WoFSCast, Graphcast-based emulator for the Warn-On forecast system. So Corey, whenever you're ready.
Hello, everybody. Let me make sure I know what I'm doing here. There's that. All right. Well, first of all, how many people here have heard of WoFSCast? Raise your hands. Thank you, Ted. Okay, that's pretty good. For those who didn't raise their hands, how dare you? No, I'm just kidding. Well, everyone will know about WoFSCast after today. So in short, WoFSCast is an emulator for WoFS, or the Warn-On Forecast System. So we need to begin with a description of the Warn-On Forecast System. So this has been developed at NSSL. It's described in great detail in this paper by Heinzelman et al. 2024. It's a, oops, wrong button. That's going to take some getting used to. Here we go. So WoFS is a rapidly updating ensemble data assimilation and prediction system designed to support weather service, thunderstorm forecasting, and warning operations, focused at 0 to 6 hour lead times. It's an 18-member forecast ensemble, 36 members for the analysis ensemble. Forecasts are initialized every 30 minutes. One of the unique aspects of WoFS is that it's run over a regional 900-kilometer domain that is not static. It's fixed over where high-impact weather is expected on a given day. Uses 3-kilometer grid spacing. Output generated every 5 minutes. It's currently run by the Weather Service in Azure for high-impact weather days. The output is available on a public web viewer linked there. It's actually been running for some of the World Cup games. It's not yet fully operational, but it's essentially been quasi-operational now for several years. It's routinely used by the Storm Prediction Center, Weather Prediction Center, and many WFOs around the country. So now what is WoFSCast? So WoFSCast is a Graphcast-based emulator for the Warn-On Forecast System ensemble member forecast. So WoFSCast doesn't currently emulate the analysis system. It doesn't generate initial conditions from which to generate forecasts, but it does emulate the WoFS ensemble member forecasts using a Graphcast-based architecture. That's Google DeepMind's Graphcast. It's trained on about 300 terabytes of WoFS forecasts from springs 2019 through 2021. What's unique about this training data set is that, well, the forecasts are actually available every 5 minutes, but we've trained WoFSCast on 10-minute forecast data as opposed to the 6-hourly data that global emulators tend to be trained on, or hourly for storm scale emulators. So by training on 10-minute forecast data, we assure high fidelity to simulated storm evolution, which is critical if you want to predict thunderstorms at 0 to 6 hour lead times. Details matter. We want to get storms in the right place. We want to get storm mode right, storm intensity right. So I mentioned the 10-minute aspect, but also the fact that we're training on forecast data is critical for reasons I'll go into more a bit later. So one might ask, well, why are you simply emulating WoFS forecast? What does that buy you if you're just trying to match what the WoFS already gives you? Well, as you may have guessed, these are all driven by GPUs, so we can run much faster and more cheaply than the WoFS. So that's the main motivation, and I'll get into some ways a bit later in which we could potentially exceed the accuracy of the WoFS. WoFSCast was run in real time in Azure during this last year, this past spring's HWT spring forecasting experiment, and I'll go into that more. So the ultimate goal with WoFSCast is to supplement or potentially ultimately replace WoFS forecasts, thereby providing more timely and accurate weather service guidance for tornadoes, severe thunderstorms, flash floods, and so forth. So I've linked a paper below on an initial version of WoFSCast, focusing on its deterministic performance out to 2 hours. So that paper is already getting outdated. And I'll acknowledge the first author on there, Monty Flora. He's really the one that got WoFSCast off the ground, did most of the initial development. And now he's off living in greener pastures in the private sector. Shocking. So as I said, WoFSCast provides faster, cheaper storm scale forecasts than the WoFS. So on the right, we have an example forecast of a squall line from WoFS. And as I've shown here, a typical WoFS ensemble forecast takes 10 minutes plus using over 1,000 CPUs at a cost of over $1,000 a day. WoFSCast, to get very similar forecasts, requires about 1 minute with one GPU node costing between $40 and $100 a day. So that's the primary advantage of WoFSCast. So how does it work? So as I mentioned, it's based on Graphcast, but Graphcast is a global emulator. So the initial step was to modify the Graphcast code, which was open source from the beginning, for the limited area unfixed domain that WoFS uses. So that took some work on Monty's part. So then to train WoFSCast, we have two inputs separated by 10 minutes. So 2 time steps of input. These are WoFS member forecast states valid 60 and 70 minutes into the forecast. So to get far enough past the analysis update to get beyond all the unphysicalities generated by unbalanced initial conditions. And then the target during the machine learning training is the forecast valid 10 minutes later. So we have 60 and 70 minutes as the inputs and 80 minutes as the target. So WoFSCast then learns how to generate the next forecast state given the 2 prior forecast states as illustrated here. So then at inference, we are, the initial inputs are the forecast analysis, so t equals 0, and then the t equal 10-minute forecast. And then like other emulators, we then roll out the forecast autoregressively. So then for the next forecast, the inputs are going to be this t equal 10-minute forecast, and then the t equal 20-minute forecast that was generated by WoFSCast, and then those 10 and 20-minute states will be used to generate the 30-minute forecast, and so forth all the way out to 6 hours. So Graphcast is a graph neural network architecture. So a graph neural network basically means that data are represented as a graph. In other words, a set of nodes connected by edges. And then, so you can see, for example, okay, let's see, I'll use these mesh nodes as an example. Imagine lines connecting these dark black dots. Those would be the edges, and then the black dots are the mesh nodes. So at each step through the graph neural network, information travels from between adjacent mesh nodes along these edges. And then you repeat that process so that information ultimately can travel as far as that needs to throughout the domain. And that information transfer is handled entirely by multi-layer perceptrons, which are the basic fundamental neural network building blocks of all of these deep learning models. So WoFSCast and Graphcast use this multi-level mesh concept where you start with a very coarse mesh. So here this would be our 900-kilometer domain. This thing is hard to aim, isn't it? Whoa. Okay, am I doing something wrong? Anyway, so if this is the 900-kilometer WoFSCast domain, you would start with these mesh nodes and then connected with these edges. And then they're algorithmically refined to greater and greater refinements until you get to this finest mesh, which has average spacing of 11 kilometers. Then you combine all of those meshes together, and the union of all those edges and mesh nodes are your multi-layer mesh, and that allows large-scale weather connections to be emulated, since with these longer edges, information can travel across a large portion of the domain in one step. Whereas if you use only this very finest mesh, you'd have to have information traveling, have to iterate through the neural network, the graph neural network many, many times for information to travel as far as it needs to throughout the domain. And with each step, you lose information. So now it turns out for WoFSCast, maybe this isn't so critical for global prediction. It definitely is. Not clear whether this multi-layer mesh provides a huge advantage versus using maybe these, this finest mesh. But anyway, I'm off track. So like a lot of current emulators, WoFSCast uses an encoder, processor, decoder framework, whereby during the encoder stage, your NWP nodes, which are your grid points, your weather variables in physical space, U, V, W, and so forth, Those are encoded into a high-dimensional latent space on the mesh nodes. So here's the encoder illustrated here. So these light gray dots represent NWP grid points, and then these black dots are mesh nodes. So once you've encoded from the physical into the latent space, your processor then transmits information between those nodes using a message passing network, and that's basically what I described before, where information travels along the edges, and then you have features at the edges and the mesh nodes that get updated with each iteration. So this is where the actual forecast magic happens. It's entirely in this multi-layer mesh latent space, which actually, again, has average spacing of only of 11 kilometers, which is pretty coarse compared to the 3-kilometer forecast that we're generating. Yet all of that higher resolution information is still encoded in the latent space. And then finally, you have the decoder, which takes you back down from the latent space to the physical space, so from your mesh nodes to your NWP nodes. And that's how you end up with the prediction of your next forecast state. So we have only three, currently, in the current version of WoFSCast, we have 6 3D predictors valid on 11 levels. WoFS uses 51 levels, but we only use 17 levels currently for WoFSCast. UVW, geopotential height, potential temperature, and vapor mixing ratio. For 2D predictors, we have composite reflectivity, so no 3D reflectivity, just composite, 2-meter temperature, and 10-minute rainfall. We have forcings that tell the network information about top of atmosphere radiation and time of year and day. And we have static fields with terrain height information and a land water mass. Importantly, the initial and boundary conditions come from the WoFS. So for the initial conditions, as I described, that's from the t equals 0, t equals 10-minute WoFS states. And then for the WoFS, for the boundary conditions, we use the prior WoFS forecast for the boundary conditions. So currently, WoFSCast is completely coupled to WoFS. Okay, so how well, now that you have some idea of how it works, how well does it work? Little spoiler alert there. So as I said, the goal is to get very high fidelity to storms, including intra-storm processes. So this is actually with an older version of WoFSCast. You can kind of tell because it's a little noisy, but it still paints the picture. So here's composite reflectivity, and then this line corresponds to these vertical cross sections down here, where we have updrafts in red, and then with the kind of convergence, divergence, dipoles, and the green contours, and then cold pools. This is virtual potential temperature perturbations. And WoFS on the left, WoFSCast on the right. Very good correspondence between the two. So in some sense, WoFSCast has learned the evolution of storms and storm scale processes pretty well. And we get only modest smoothing as the forecast rolls out. One common weakness of emulators trained with MSE loss is that they tend to smooth out over time. We don't really see that with WoFSCast, and this is because WoFSCast is trained on very fine temporal resolution data, 10 minutes. Perhaps even more importantly, it's trained on forecast data. So if we try to train on analyses, the results actually get further from reality and the results get smoother. It's because analyses contain, at these scales, locally very large errors. And so the true atmospheric evolution at these fine scales is not accurately represented in series of analyses. The WoFCA system is pretty sophisticated, but it's still not good enough to ensure realistic evolution of the analyzed atmospheric state at 10-minute intervals. Whereas with forecasts, you're training basically to emulate the model itself. So the signal to noise ratio is essentially infinite. You're not having to learn through any noise. So that's the key to WoFSCast success. But it does mean in its current state that it cannot exceed the forecast skill of the WoFS. And illustrating here, the benefits of not having excessive smoothing in the forecasts. This is the Hill Country, Texas flash flood tragedy from last year. WoFSCast on the left, WoFS on the right, and you can see that WoFSCast is able to, oops, wrong button again. WoFSCast is able to generate very high rain rates. These are 6-hour ensemble 90th percentile rain rates exceeding 10 inches, just as in the WRFs. And as I mentioned, WoFSCast was evaluated subjectively in this year's spring forecasting experiment. So we have on the left 0 to 3 hour ensemble reflectivity ratings from participants, and then 3 to 6 hour ensemble reflectivity ratings. And these violin plots are very similar. There's essentially no difference in how participants rated the traditional WoFs and the WoFSCast. But when you dig into the comments, and we saw this last year as well, you see something interesting. So again, people said WoFSCast was very competitive with the WoFs, but they also acknowledge that WoFSCast smoothing does show up. I mean, it's a lot better than a lot of other emulators, but there is still smoothing that increases with lead time. And this smoothing has the fortunate effect of offsetting the well-known storm frequency bias in the WoFs and other ARW models. So in cases where the smoothing resulted in fewer storms in WoFSCast than in the WoFs, this was as often viewed favorably as unfavorably. Favorably in cases where it was right for the wrong reasons, where the WoFs had a high frequency bias, but sometimes unfavorably when the WoFSCast was missing too many real storms. But it kind of averaged out, as you saw in those subjective ratings, where WoFs and WoFSCast were rated almost identically. Now, I've since done some objective verification for those same SFE forecasts, and they support the subjective results. So we see with these purple, well, I should say these are object-based matching verification plots generated using the Skinner et al. 2018 method, where you use simple criteria to identify storm objects and WoFs, WoFSCast, and MRMS, and then you match them and generate contingency stats shown here. So purple is frequency bias, and we see the high bias, and you want to look at the right axis here for frequency bias. So we see the very high bias in WoFs, much lower bias in WoFSCast, which ends up being a good thing, especially in the beginning of the forecast, but then frequency bias falls below 1 in WoFSCast later in the forecast. So correspondingly, we have a higher success ratio in WoFSCast, a slightly lower POD, that's the red curves, in WoFSCast. I should mention that WoFSCast is dashed, WoFs is solid. In the end, though, the CSI is pretty similar between the two systems, again in line with the SFE ratings. These are, in red, we have false alarm counts, and then in blue, we have hits in the two systems. So we see that WoFSCast has far fewer false alarms than WoFs, which is good, and then slightly fewer hits than the WoFs, which is bad. But so again, these effects kind of offset each other fortuitously. So the fact that we are not perfectly emulating WoFs is actually not necessarily a bad thing, which gets kind of awkward, as I'll show later. And then here's ensemble fraction skill scores for 3 different neighborhoods, again showing WoFSCast in green being pretty competitive with WoFs at all lead times. And so, getting back to what makes WoFSCast special, the fact that it's trained on on forecast data. Well, here WoFSCast does get butterflies. I'm riffing off of a title of a paper by Sells and Craig 2023, where they pointed out that the global emulators trained on the ERA5 reanalysis, they're incapable of learning the growth of low amplitude errors because the growth of low amplitude errors is simply not present in the ERA5 reanalysis data set. It's masked by unavoidable errors. But WoFSCast does not suffer that limitation because our training data are, in a sense, perfect. We're training on forecast data. There are no errors in that sense. And so we can get rapid perturbation growth, unlike in those other models. So here, if you introduce infinitesimal perturbations to the initial state, WoFSCast rapidly, at all scales, grows those perturbations in the manner you would expect. So for similar reasons, WoFSCast forecasts are relatively sharp, despite the fact that the current version of WoFSCast is trained with MSE loss. That said, and as participants noted, there is still room for improvement because WoFSCast does still suffer some smoothing. I say room for improvement in the sense that we can get closer to WoFS, but again, it's not clear if that practically is a good thing or not. I'll get into that more. So lately, well, for a while now, I've been trying to train WoFSCast with CRPS loss, continuous rank probability score. So this is one of the two main methods that emulators use to produce sharper forecasts and better ensemble spread. The goal is to sharpen forecasts by avoiding the double penalty associated with MSE loss, where for high gradient, highly intermittent fields, small phase errors are going to be penalized severely. So the emulator simply learns to generate smoother forecasts and thereby achieve lower mean squared error. CRPS avoids that problem. So I'm basically following the approach that the ECMWF AI forecast system used with some modifications to control the compounding noise growth during rollout. That's what makes CRPS training non-trivial. You have to find a way to control the noise because you're actually injecting noise into the model during training. So yeah, during training, you're actually generating mini ensembles, and in my case, I'm using ensemble size of 3 via latent noise injection, which I don't have time to get into, and then inputting to the almost fair formulation of the CRPS loss that accounts for the fact that you're using small ensembles rather than a continuous function. And then at inference, you have the option of then initializing as many forecasts as you want from the same initial condition and varying the random number seed to generate different forecasts. So how much does CRPS loss sharpen the WoFSCast forecasts? Let's see, so starting up here, these are quantile plots of 10-minute rain rates. The MSE trained WoFSCast or base is blue, and the CRPS trained WoFSCast is green. So we do see sharpening, and this shows up in other variables as well. We do see the forecast getting sharper. And then if you look at ratios between vertical velocity spectra between WoFSCast and WoFS, where we'd like to see at all scales, we'd like to see this ratio be 1 if we're perfectly matching WoFS spectra. The MSE train model is pretty good already, but compared to the CRPS train model, we do get these 10 and 60-minute curves to be much closer to the unity line. So again, consistent with what we see up here. The forecasts are getting sharper, but then as you get all the way out to 5 hours, you actually end up with excess energy. And again, this is the noise buildup that I'm trying to control. But it doesn't really seem to manifest qualitatively in the long-term forecast, so maybe it's okay. So by training with CRPS, we obtain a WoFSCast version that better preserves storms, but as one might expect, it better preserves both real storms and spurious storms. So if we look back at storm object hits versus lead time and false alarms versus lead time, MSE trained WoFSCast in blue, CRPS trained WoFSCast in green, we see more both real storms being preserved in the CRPS trained WoFSCast and spurious storms. So on net, maybe this is not an improvement, even though we are actually better emulating the WoFS. Again, because WoFS has this strong positive frequency bias in storms, better emulating WoFS is not necessarily a good thing. And then this shows up here in the Skinnerology object-based matching verification, where again, frequency bias is higher in the CRPS trained WoFSCast, that's the dotted line, versus the MSE trained WoFSCast, the dashed line. But then you get the corresponding, you get an increase in POD, very small increase in POD, very small decrease, which you can't even barely see here, and success ratio, and then the CSI is basically a wash. But does it improve ensemble spread? So here we have animations going out to 5 hours or so of WoFSCast forecast generated from the same initial condition but with different random number seeds. I think most people in here would say you're not getting a lot of spread. Here's truth, or the WoFS member forecast for this case. You're not seeing a lot of spread between these three. But this does make sense because the baseline MSC-trained WoFSCast is already really good at emulating WoFs, so you shouldn't get a lot of spread in these forecasts. But what this means is that currently for our WoFSCast ensemble member forecasts, the initial condition diversity is the dominant source of the forecast spread. So we initialize WoFSCast from 18 WoFS initial conditions. That provides much more initial condition diversity than varying the random number seed and generating multiple forecasts per initial condition. But it is worth exploring other multimodal approaches to try to further expand the spread. So here I'm showing plots of spread error and spread error ratios. These are for storm locations. So ideally this ratio would be 1 where spread is matching the error. So WoFS is in black, and then the MSC-trained WoFSCast is in red. The CRPS-trained WoFSCast with 18 forecast members is blue. And then in green, this is a 72-member forecast where for each of the 18 initial condition members, you generate 4 different realizations from that member. And you can see the blue and green curves are pretty much on top of each other, and they don't quite match the WoFS ensemble spread. So yes, we need to look elsewhere to try to improve the WoFSCast ensemble spread, but it's already really close to WoFS and much better dispersed than other emulators at these scales, especially. So yeah, so at this point, okay, is CRPS really adding anything? Well, this is where it may actually come in much more handy. So I've recently delved into this notion of hybrid observation state prediction, where the goal is to add additional predictors to WoFSCast, observation-based predictors. So for example, MRMS composite reflectivity, QPE, and azimuthal shear. So a driving question is how close can we get to the amazing NVIDIA StormScope performance? So NVIDIA showcased their 0 to 2 hour emulator in the testbed this past spring, and it was just amazingly good. Where they have several GOES fields, and then they have MRMS composite reflectivity, and they show they can predict MRMS composite reflectivity very well out to a couple of hours or so. So how close can we get to that with our architecture? So to do this, we simply add these MRMS fields to WoFSCast. They do require a bit of different treatment. We actually add some recent, in this case, MRMS composite reflectivity states as forcing. But other than that, they're treated exactly the same way as any of the other WoFSCast fields. And what I found so far is that when comparing these MRMS predictions to the default WoFSCast reflectivity predictions, which are trying to emulate what the WoFS composite reflectivity forecasts look like, we do see substantial improvement. Success ratio and CSI are much improved, but we do have too few storms, as indicated by this frequency bias line being well under 1, and POD isn't really improved. So this is because the composite reflectivity forecasts so far are too smooth. Oops. As illustrated here, we have MRMS obs on the right, we have the WoFSCast predictions of MRMS in the middle, and then we have the default, and then we have the WoFS reflectivity forecast on the left, and the WoFSCast reflectivity forecast would look very similar. But we see better correspondence between these two, but clearly the fields are too smooth. This is expected given that this is still using MSC loss, and MRMS is going to be influenced by non-meteorological variables that the emulator does not know about. So using MSC loss, it will tend to want to produce smoother forecasts of MRMS reflectivity and other observed fields. Oh, I can't go back. But that's where CRPS loss comes in, and I've got a training run going right now where hopefully we can still maintain better performance of the MRMS predictions than the default reflectivity predictions, but with much better sharpness. that makes that field resemble WAF's MRMS observations a lot better. And then finally, I've also recently added some new fields to WoFSCast, and more will be added. So this is ML Cape, so WAFS versus WoFSCast, and then this is Hailcast diameter, WAFS versus WoFSCast. Basically, any of the fields that we already have in our WAFS files, we can train WoFSCast to predict those fields as well. There are various flavors of CAPE, SIN, shear, storm relative felicity, supercell composite parameter, significant tornado parameter, hailcast, 0 to 2 kilometer UH, and so forth. So what's next for WoFSCast? So we're going to continue incorporating these observation-based predictors along with these additional storm attribute and environmental fields. The major next step is training a 1 kilometer WoFSCast, which will unlock real-time thunderstorm guidance at unprecedented resolution. Here again, we're going to be leveraging our existing WoFS catalog to generate the training data for this new 1 kilometer emulator. It actually, I think we're already over halfway through rerunning a bunch of our 3 kilometer WoFS cases at 1 kilometer grid spacing. So hopefully I'll have some results for that by the end of the calendar year. We'll see. AI-assisted or AI-based data assimilation is becoming a major focus in our group, not just around WoFSCast, but just in general. So this will ultimately improve the WoFSCast initializations and thereby improve the WoFSCast forecast, and then eventually allow us to decouple the WoFSCast from WoFS. Since currently we rely on WoFS for the ICBCs, in the future that will no longer be the case, and since WoFSCast is so cheap to run, that would mean that hopefully we can run WoFSCast much more often than we run WoFS. And finally, hopefully not too far in the future, WoFSCast will be implemented in NOAA-EAGLE. That's the Experimental AI Global and Limited Area Ensemble Forecast System. It's basically like the AI quasi-operational analog to the UFS. So this would at least allow WoFSCast to run whenever the WoFS runs. And I am done. Thank you.
All right, we have time for a question or so for Corey.
Yeah, great talk. So I have a question about the architecture. So we have a Google imposed limitations on the vertical resolutions and model tops. Did you guys have tried to go beyond the 31 levels and model top increasing to 40 kilometer, for example?
Well, and here we're only limited by the WoFS model top, which I don't know, Lou, I don't know offhand how high that goes for the ARW WoFS. Do you know, Lou? The model top in kilometers. Okay, 20 millibars.
Because we actually have to get data to put it.
Yeah.
Or it might be 10, and it's something like that. Maybe it's even.
But we do. So we have 51 vertical levels in the WoFS training. So conceivably, we could develop up to a 51 vertical level WoFSCast, but it's probably not necessary to get the variables that we want the most.
Cliff, close us out.
Yeah, hi. Yeah, thanks for the talk. Extrapolating things is valuable. Okay, it's certainly very useful, but the paradigm, the highest level is to create new convective areas that are significant. So my question is, how does WoFSCast do in creating new major convective areas that didn't exist before?
Well, that is the challenge facing, I think, all storm scale emulation. Right now we can train on forecasts, we can train on current storm scale analyses. Obviously, as I said, training on forecasts does not allow you to get beyond the dynamical model that you trained on. Training on analyses doesn't get you any further, at least at these very short lead times, because the errors are so large. If we had a high enough quality storm scale reanalysis, then conceivably we could, transcend the forecast skill of any of our dynamical models. But I don't know if it's even possible to achieve that. I think we should strive for that. But
can you generate new major convective areas?
Yes, currently, the current WoFSCast cannot.
Cannot. That's very important.
Yeah.
It cannot create a new major convective area. It's only extrapolating things that it has.
Oh, I see what you're saying. You mean like forecast storm initiation? Is that what you?
Storm initiation.
Oh, okay.
Or can it do
I thought you were talking about like different regimes
no.
that. Okay.
I was shocked by your answers. So you're saying you're saying that it can generate.
Yes, it is able to forecast storms that initiate during the forecast, but no better than the WoFS can. So it's and the WoFS, like all storm scale models, does struggle with that.
Not worse than, but not.
And that's something I've started to look into. I would say at this point it's mildly worse than WoFS.
Okay, thank you.
Only mildly.
Okay, thank you.
All right, well, let's thank Corey once again. That concludes the talks for this afternoon. Doors will open at 7:45 tomorrow morning, and session will get started with opening remarks here at 8:30 tomorrow morning. So have a good night, everybody. See you all then.